Hi, everybody. This is our first actual lecture. It is on Chapter 3, Vectors, and I'm going to talk a little bit about physics first and introduce it. But before we do that, I wanted to show you a few important things in our course and in your ebook. So this is our Canvas website. And when you go here, if you click on Wiley Course Resources, you know that you have the e-textbook. So we'll come up here first. And in the e-textbook, assuming you've got it going, you can go and you can choose, I always forget which one it is. It's the very top. You can come down and choose, we're doing Chapter 3. Chapter 3 has 3 sections, 1, 2, and 3, which we'll go through those. There's a review and summary, which will take you through the equations and kind of the overview of everything once you're done. There are some questions that you can practice with and go through, and then all the problems from the text are here, okay? So keep that in mind. When you go back to the book, at the very end of the book, there are answers to the checkpoint questions and the odd number questions, okay? Just so you know. So you can come through here and, check yourself. But there's something much, much more important. In the course resources, there is a tab called course-wide resources. In here, and as you can see on my screen, they should all be visible to you. Sorry. I have a bit of a cough right now. But here, you have video sample problems that you can go to. You can click on Chapter 3. It'll take you through, and it does like a Khan Academy style sample problem if you want. And they're the sample problems from the chapter. You can also go to the student solution manual. So if you want to do any of these problems, any of these odd problems, they will tell you how to do them, how to solve any of the odd problems. And I might assign them for homework. So if you're doing an odd problem in the homework and you're struggling, some of these problems are right here. They're not obviously all here, but there's quite a few of them here. And there's also, furthermore, additional sample problems, animated illustrations, this flying circus of physics, math help tutorials, simulations. There's all this wonderful stuff here, okay? So it's really up to you how much you think you need, how much you want. You could, A, watch my lectures and study them and then do the homework. B, you could read the problem or read the chapter on your own, do some of the sample problems, make sure you get it, and then do your homework. C, you can use all this stuff if you're really struggling, or some combination. And I know that it can be a little bit daunting when you're given a bunch of options to figure out which one works for you. But I want you to have this because you really, really have to do a lot of problems until you get this stuff down. I said it last week, but doing physics is like playing piano or working out or any skill that you develop. The more you do it, the more you get wrong, the more you have to struggle, the better you get at the end of the day. None of this stuff is do one problem and you got it. It's like doing math in that you got to do 30 or 40 of them before your brain really understands it. And a lot of these problems are unique. So you may see something in a problem that you will never see in another problem. So it'll help you to kind of develop your strategies for solving any type of problem. Now, I should also note that vectors, this chapter, is a lot of math. And it's a lot of the math that we'll need that'll be kind of in the background. We're just going to assume that we understand it and use it for everything that we do. So it's not so much real life or a class of problems. This stuff we're going to use over and over. And specifically, we're going to use multiplying vectors at different times. There's something called a dot product and a cross product. And when you dot two vectors, you get a certain answer. When you cross them, you get a different answer. And they apply to different problems. And you'll see that at the end of this lecture. But just know that this lecture is going to be pretty math heavy. You might not understand it all if you haven't had vectors before, and that's okay. Think of this as almost a reference chapter in some ways. And then once we have it, we're going to use it over and over again for the rest of the course. And I'll explain that in the official start of this lecture. But I just wanted you to see, I'd forgotten where these resources were, that these resources are all here for you. And if you don't want to use them, that's fine. But if you need to use them, use them. They'll help you learn. They're here for you to learn. This is why we have an e-textbook. It's so that we have all these integrated, cool simulations and little lectures and all that stuff. And I understand that my method of lecturing may not 100% work for you. And maybe these Khan Academy style lectures will help you more, okay? And then finally, if you're really struggling with something, what I ask you to do is I ask you to give it a shot. Try to get as far as you can and figure out what you're doing wrong and what you don't understand. And then text me or ask me a question during the lecture, during the Zoom meetings, okay? Or ask your other students in your class, ask your lab partners and see if they can explain it to you. When you do that, you're helping them and you're helping yourself. And if your friend doesn't understand how to do it, explain it to them. It actually will help your understanding of these problems. Okay, so I just wanted to kind of show you where these things were. I'll show you again tomorrow during the lecture part and show you some cool stuff. And we might even go back into this at the end of this lecture and do a few of these practice problems or something, okay? But they're here for you. I encourage you to use them if they help you. If they don't help you, ignore them. But there's also some cool stuff, and some of this may even go more in depth than we will in the material of the course. So there's a lot of cool stuff here. Enjoy it. Hopefully you'll find it interesting. More than that, hopefully you'll find it useful. Okay, so let me go back to the PowerPoint, or let me go to the PowerPoint and get this lecture started. Close a couple things here. Okay, so this lecture is on Chapter 3, as I said. I'm going to loosely follow the book. I'm going to cover everything that's in the book, but I'm going to kind of do it in a way that makes sense to me. Sometimes your book omits information that I think is important, or it goes into too much detail on things that you don't really need. So we'll try and go through it. I'm going to derive a little bit here and there, and I'm going to try to show you some sample problems. It may feel like we're not doing a lot of problems. We'll do problems at the end, and hopefully you'll get it. And then the point is to introduce you to kind of the standard problem, let you do the homework, and the homework will be a little bit harder than these problems. The point of that is I want the homework to be hard for you guys, because you can always look it up on Chegg. You can always look at the Student Solution Manager. You can always get help from somebody to get through it. It should be hard. That way, when you get around to doing problems on the exam, they're easy. You know, the exams are kind of like a, where you in like chemistry or in a lab, where you do a practical and you just demonstrate how to solve a problem for me, okay? They're not super easy, but they're not meant to be tricky. The homework problems are tricky, and I know that, but that's intentional on my part. I choose problems that are either A, really good fundamental examples, or have some trick in them that I want you to at least see once, okay? All right, and here's the other thing. You cover vectors and vector multiplication, I believe, in 3A or 4A or one of those. You might not have had vectors too much yet. It's okay if you haven't. we're going to cover what we need. So just note that that's okay if you don't really remember or if you're bad with them for some reason. We're going to cover them. I'm going to try my best to explain them in great detail, and hopefully you'll be comfortable after this lecture. So in physics, there are quantities called scalars, and there are quantities called vectors, and there are also quantities called tensors, which thankfully we won't have to deal with them in class, and things like matrices and all these other mathematical objects that you may not be too familiar with. But the main thing is that in physics, well, I'll talk about this in a second, but basically the main thing is that a scalar is just a number. It's a quantity. So a scalar is a quantity, and it's a quantity like energy. It's a quantity like money. It's a quantity like, I don't know, how many people. It's something that is, in general, is just a thing, okay? It doesn't have a direction, it's just a quantity. A vector, on the other hand, is an arrow, okay? It's an arrow. It can point in any direction, but the arrow has a length, which is what we call a magnitude, and it has a direction. It points in a definite direction. The idea, though, is that if you have, let's assume that this piece of paper is some XY plane, that we can pick this vector up and put it anywhere we want in our XY plane, and as long as we don't shrink it or make it longer, and as long as we don't rotate it at all, it's the same vector. We can move them around wherever we want. So vectors have a direction, they have a magnitude, and that has to be preserved in your math and in your drawings, okay? Vector quantities are things like the velocity, the direction that a car is traveling. It's traveling 5 meters per second north. If you just said it's traveling 5 meters per second without specifying a direction, that is a scalar. So a vector has to have a direction. And that's super important, okay? A scalar has no direction, it's just a magnitude, right? So that begs the question, why do we even need this? Why can't we just do numbers? Why can't we just multiply things and divide things? Why do we need some weird vectors? And here's the funny thing. Number one, remember that we are studying motion in this class. Everything that we're doing in this class, all 15 chapters, what we're trying to do is model how an object or a collection of objects moves and make some kind of prediction about where it's going to end up, or maybe figure out where it started from. But everything we do has to do with motion. That's why this is actually called kinematics and dynamics, which are both the study of how objects move, okay? And therefore, we need to come up with a way to mathematically describe motion. And it's not as simple as it seems. However, because of that complication, what really, really good mathematicians realized is you can make a simple diagram that conveys all the information you need. Now humans, and I said this when we talked about graphs, humans don't like a lot of complexity. We're actually not very smart. The simpler that you can make something, the better. And one thing that we do really well as a species is we understand visuals. We are visual learners. We completely see visually. And so if I gave you a bunch of equations that were solved and said, oh, here's the answer, a lot of you may not understand it, or it may take you a while to understand it. However, I can draw the motion and you totally get it. And so as an example, let me give you a quick example. Let's say this is an origin of an XY, right? It's an XY plane. And I tell you that you travel north like 5 meters, and then you travel east like 4 more meters, and you travel southeast like 3 meters, and You travel, southwest 5 meters, and then you travel back 6 meters west, and you get back. You can see immediately from this that you get back to the origin, that you went nowhere. You went somewhere. You traveled a long distance, but you actually are, your new position is at the origin from the picture. I could have you add and subtract all these vectors and do them component-wise, which if you don't know what that means, we'll talk about that soon. But this picture conveys that without having to do any math. You can turn it into a mathematical model, but you don't need to because you can draw it. So a lot of times what we'll draw is, imagine we draw an object in free fall. We'll draw a vector that says v, which tells us that the velocity is downward. And let's say it's 3 meters per second. So we know that this is traveling downward. We can also draw an acceleration vector. We could draw like a height vector. We're using vectors as a way to draw what is happening in our system. And then we're going to turn those vectors into math. So we're going to turn these drawings of arrows into mathematical equations. Pretty quickly, we're going to be doing free body diagrams. And that's exactly what we'll do on the free body diagrams. We'll draw vectors and we'll figure out from the vectors what the equations are, okay? So that's the whole reason that we're using them. It turns out, however, for those of you that are really good at math or have had a lot of math, vectors are a very elegant mathematical system. And they're probably something that you haven't yet encountered if you haven't gotten to them. And that's that they have their own set of rules and postulates and identities that govern how you can multiply them, how you can add them, how you can subtract them. What happens when you multiply by 0? What happens when you multiply by 1? Vectors do not completely act the same way that the normal numbers do. Certain weird things happen when you multiply vectors in certain ways that don't happen with normal numbers. And we'll talk about that. But it's a very, very elegant system. And not only that, you probably don't realize this, but vectors actually aren't just motion. For those of you in computer science, you're probably already familiar with vectors. When we have a collection of data in a column, we call that a column vector. And there's things called matrices, which are made up of rows and columns. And those act like vectors, and they allow you to very quickly, using a computer, understand or solve equations involving those vectors. Vectors are used in almost every field of science. So if you don't understand them yet, just realize that you're going to use them because they provide a visual representation of motion, or they provide a bunch of components. And we'll talk about both sides of that equation, or both sides of that idea, that a vector can be a drawing and it can be a bunch of components. But it turns out that vectors are not going away for you. If you're going to be in science, you're going to need to understand vectors forever. And they're going to take different forms. Sorry, that's my dog scratching herself. Go play, babe. Go play. Get out of here. Okay, so before we talk about vectors, I want to go back and review something that I also find kind of odd and kind of funny. I don't remember when I studied trigonometry. It might have been in 8th grade. It might have been in algebra. I don't know. But I felt like once I got to physics, I had to teach myself trigonometry all over again. We need to remember what we call right angle trigonometry. You need to make sure that you understand it, that you understand things like sine, cosine, tangent, and the inverse of those functions, which we'll talk about here. Because once you understand how right angle trigonometry works, you can break any vector up into its components, okay? So what right angle trigonometry is if you have a triangle with a right angle, meaning a 90-degree angle line, Okay, you know that this triangle has a hypotenuse and it has an x and a y, right? And you probably remember that x is actually h. If this is an angle, theta, this is, getting a little ahead of myself. So x is equal to h times cosine of theta, and y is equal to h times sine of theta, right? So given a hypotenuse and an angle, you could tell me what this length y is and this length x is. Similarly, for this same triangle, okay, we could take this angle, which is phi, and now if you turn it, if you think about it as being turned, here, if this is still h, x is equal to h sine of phi, and y is equal to h cos of phi. And therefore, in these, you note that cos of theta is equal to sine of phi, and sine of theta is equal to cos of phi. Furthermore, they have to equal 180. So 180 degrees is equal to 90 plus theta plus phi. So all the interior angles of a right triangle have to equal 180 degrees. Sometimes we're going to use radians, and I'm going to say it here, but we'll constantly be going back to this. If you ever need to turn degrees into radians, one thing to remember is that there are 2 pi radians in 360 degrees. So if I want to turn 180 into radians, I would multiply 180 times 2 pi rad over 360. This would be a half, so I would get pi rads. There are pi radians in half of a circle. Now, one thing I do want to say about radians and degrees, degrees are completely made up human units. They're not real units. And when we talk about units, as we start going, they're not real. They don't have any real units. Radians are a pure number. So on your calculator, a lot of times it's fine to use degrees, but anytime that you need to get a number, make sure you're in radians. And we'll talk about that more as it comes up. But okay, so here we're going to do something that you may or may not know. And if you already know, just bear with me. But if this is my angle, and this is h, and this is x, and this is y, there's something called SOHCAHTOA. SOHCAHTOA, okay? X is the adjacent to the angle. Y is the opposite of the angle. And so what we do is we write that sine of theta is equal to opposite over hypotenuse, or y over h. Cosine of theta is equal to x over h, adjacent over h. And tan of theta is equal to opposite over adjacent, or y over x. And if we went back and looked at phi, right, it would flip these, right? So sine of phi would be x over h, and etc. Just so you know, okay? Now, why do we need to know this? Well, if we knew the hypotenuse was 2 and the y was 1, let's say, so let's say we know that y is 1 and h is 2, okay? We could find what the angle is from this equation. There's something called an arc sine and an arc cosine and an arc tangent. And if I take the arc sine of both sides, you'll see these on your calculator. They're sometimes written with a -1. That is not an exponent. That is an arc, or the inverse of sine. When you multiply the inverse times normal sine, they cancel. So you get that the angle is arc sine of 1 over 2. Now let's look at this with our calculator. If you have your calculator, grab it. If you don't, my calculator right now is in degrees. And if I take arc sine of 1/2, I get 30, okay? Which means it's in degrees. Now, quick quiz. What is 30 degrees in radians? Well, 30 degrees in radians would be 30 times 2 pi over 360 or pi over 180. 30 goes in 6 times. This is pi 6. So pi 6 rads. You could put degrees, and rads here if you want to do the unit analysis. But if I do that, if I put my calculator into radians, and then I do arc sine of 1/2, it gives me 5.5236-ish. If I do pi divided by 6, I get the same number, okay? So it gives you pi 6, right? We're going to have to use that a lot. Sometimes we're going to end up using this particular idea a lot. And so if you're not used to doing inverse functions, make sure you know how to do it, okay? So you have all these nice things. And the really cool thing here, though, is that if I make a new slide real fast, and I go to draw, now imagine I have a vector that is, I tell you, is 5 meters long at an angle of 45 degrees. Let's not use 45, let's use 60. 60 degrees to the x-axis, right? This is my r vector. And what I want to know is I want to know what this length is, and I want to know what this length is. So I'm going to call this rx, and I'm going to call this ry. Well, I know that rx is r cos of theta. And I know that ry is r sine of theta. Now this would just be 5 times cosine of 60. And here's something I want you to get used to doing. A lot of you are going to want to go to med school or go to engineering or what have you. And I have a huge piece of advice for you as a student. Most of the time that you waste on an exam, you actually waste with your calculator. And if you're struggling with your calculator, you're just wasting time. So the least amount of time you can take to use your calculator, the better. And that means, if you can, learn to do math in your head, learn to do shortcuts. One shortcut that you can do is let's look at just the angles, okay? And furthermore, let's look at sine and cosine of the angles. So we're going to divide this up into 5 angles, okay? We're going to divide it 0 degrees. This is 30 degrees. This is 45. This is 60, and this is 90, okay? This is my y-axis. This is my x-axis, and this is my origin. Now, I want to know what sine and cosine of 0 degrees is, what sine and cosine of 30, what sine and cosine of 45. Cosine of 0 is 1. So this is cosine of 0 and sine of 0, okay? This would be cosine of 0 is 1. Sine of 0 is 0, okay? So you know at 0 degrees, at 0 degrees, cosine of 0 is 1, sine of 0 is 0. At 45, these are both root 2 over 2. Or another way to write them, if you multiply the top and bottom by root 2, you get 1 over root 2, okay? So these are 1 over root 2 if you want. Either way for 45. At 90 degrees, cosine of 90 is 0, sine of 90 is 1, okay? And then finally, at 30 and 60, we have to figure out a way to deal with 30 and 60. So let's do this. Imagine you have a triangle that is at 30 degrees. You can see at 30 degrees, x is going to be bigger than y. You only have 2 things to choose from. You have a half and you have root 3 over 2. Root 3 over 2 is bigger than 1/2. So cosine of 30 is root 3 over 2. Sine of 30 is 1/2. Here, at 60 degrees, you can easily see that y will be bigger than x, and therefore this is root 3 over 2, and this is 1/2. So let me make a chart here. So at the angle 0, 30, 45, 60, and 90, cosine of that angle and sine of that angle. Okay. And the only ones we have to choose from are 0, 1, root 2 over 2, root 3 over 2, or 1/2. Those are the only ones you need to remember for these angles, okay? At 0, this is 1 and this is 0. At 90, this is 0 and this is 1. 45, they are both root 2 over 2, root 2 over 2, in radians, I should say. And at 30, this is 1/2. At 60, this is 1/2. This is root 3 over 2. This is root 3 over 2. If you can remember those, you can kind of estimate your answers, or if on, say you're doing an MCAT, and they give you some trigonometry that you need to remember, and they say, oh, well, it's 8 times sine of 30. You get out your calculator and you try to put it in sine of 30, and then you realize you're in radians and you wasted a whole bunch of time. The person who's remembered this goes 8 times sine of 30 is 8 times 1/2, that's 4. And they're done. And they saved themselves a minute of messing with their calculator. Furthermore, these same angles are the same as you go around, okay? It's just the signs change. So 30, 45, 60, 90, 120, 135, 150, right? 150, 135, 120, 90, 60, 45, 30, 0, 180, right? And as you go around, they have the exact same value. So you only need to remember the first quadrant. At 150, cosine of theta, cosine of 150 is negative root 3 over 2, because x's and the cosine values are negative on this side of 90 degrees. The y values are still positive, right? So negative 3 over 2, 1/2. Root 2 over 2, root 2 over 2. 1/2, root 3 over 2. 0, 1, and on and on. So you can remember just that quadrant and then check your signs. It's actually super easy. That's a total aside, but if you don't know your angles, instead of using a calculator, a lot of times you'll get questions that have a 30 degrees or a 60 degrees or a 45. And always, at the very least, remember that cosine of 0 is 1, sine of 0 is 0, cosine of 90 degrees is 0, or cosine of pi half is 0, and sine of 90 degrees is 1, okay? Cosine of 180 is negative 1, sine of 180 is 0, cosine of 270 is 0, sine of 270 is negative 1, on and on and on, okay? Just make sure you remember those, which leads us to our next idea, okay? And that's that vectors have components and unit vectors. So let's say this is r and this is theta, and r lies along some theta angle to the x-axis, and this is our y-axis, okay? Now, I'm drawing these little triangles or little accents on top of these. And what these mean are unit vectors. So we can write r as r x hat plus r y hat. And that's very important, okay? It is actually the same, and we're going to see that on the next slide, but this is actually the same as just writing r. You can write it in either form. But what is r x hat? Well, r x hat is r cos of theta, whatever this angle is from this axis. And what is r y hat? Well, that's r sine of theta, okay? And what is r in terms of those? Well, here, from right angle trigonometry, you know the hypotenuse squared is equal to y squared plus x squared, or the square root of rx hat plus ry hat, and these are both squared, okay? So that means that r, the magnitude of r, is r cos squared theta plus r squared sine squared, right? But if I rearrange and distribute, this becomes r squared cos squared theta plus sine squared theta. And if you don't know your trig identities, throughout this semester, as we need them, I will give them to you, but you should know them. There's a whole bunch of things like double angle formulas and angle addition formulas and blah, 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 blah. We're not going to go over those today, but as we need them, I'll give them to you. We'll need them pretty quickly here. Anyway, cosine squared plus sine squared is equal to 1. That's the Pythagorean theorem. That means that this r is equal to square root of r squared, which technically means r is equal to plus or minus r. But we're going to assume that that just means r is equal to r. Okay, so those are our components. We need to remember this is always true. And I'm going to show you that this is always true. Okay. Furthermore, I'm also going to show you that r is equal to r y hat plus r x hat as we go further. Okay, so graphically, if I do my y and my x directions, and I start at the origin, and let's say I go some r cosine, so I go some rx distance, and then I go some ry distance, right? Where have I arrived at? What is this point? Well, this point is r away at some angle of that. How would I find that angle? Well, how would I find r, first of all? I would find r by finding what rx squared is plus ry squared. And I'm going to leave off those little things. These subscripts just tell you that that means rx means r cos theta, ry means r sine theta. Then, furthermore, if I want to know what the angle is, remember that tangent of the angle, SOHCAHTOA, tangent is opposite over adjacent. This is ry over rx, which is r sine theta over r cos theta. Sine over cos is tangent, so that is true. But if these were numbers, you could get that theta is arctan of ry over rx. Now here's a problem though. Tangent is something called oh, why is my brain? It has multiple value, it's multi-valued, which means, let's imagine that I give you that rx is 3 and ry is 4. I'm sorry, is -3 and ry is 4. Put that into your calculator right now and make sure you're back in degrees. I want it in degrees. So in mode, I go back to degrees. I get arctan of my angle is arctan of 4 over -3. So put that in, -4 over 3, and I get -53 degrees. Okay. Why am I getting -53 degrees? Right. If I draw this, okay, my origin would be here, and I would have to go -3 and then up 4. So this, you can clearly see, should be somewhere past 90 degrees. It's in the second quadrant, right? -53 is actually down 53 degrees below the x-axis. So what are you supposed to do? Well, one thing to do is either draw it, or two, add 180 degrees to it. And I get 127 if I round. So this is really 127 degrees. Just bear that in mind. Tangent is multi-valued. It gives you one of two values. Whenever you have a negative sign, Actually, anytime, because it doesn't know if the negative sign's in the y or in the x, right? And that means it changes which quadrant it's in. So it can be one of two quadrants. Also remember that because tangent is sine over cosine, at 90 degrees, sine is 1, but cosine is 0. So tan of 90 is infinity, right? Tan of 0 is 0. But the closer you get to 90 degrees, the greater tan gets, and tan actually blows up. So just know that. If your calculator gives you an error, try it. Put arctan of 90, or put tan of 90 into your calculator, and it tells you a domain error. If you put arctan of some really big number, just put like 7 nines in there. It gives you 89.999999 degrees. Okay, so tangent goes to infinity. It's multi-valued, or it goes to infinity at 90 degrees and 270 degrees. It's multi-valued. Sometimes when you're doing Wiley plus, you will forget that tangent is multi-valued, and it'll keep telling you it's wrong, but that's because you've got the wrong angle in there. And if you're in radians, instead of adding 180 degrees, add pi radians to it, okay? That's important. So we've done one thing, but I want to show you the other thing. So we said that, and I'm just going to do these, and then I'll draw in red. Okay, so this is my y-axis, and this one's my x-axis. And if you look here, I went rx and then ry. But what if I went ry and then rx? Would I arrive at the same spot? And the answer is yes. Okay. This is the exact same r as this one, which proves that r is equal to rx plus ry, and it's also equal to ry plus rx. That's the summation rule. That means that you just can add in any order. You can do addition in any order you want, okay? Any order you want. You can add all the components. There's no preferred order. You will get the same answer. That also means, okay, that if you have multiple vectors that you're trying to add, which is what we're going to do next, they also add in any order. You just add them. There's no, just like normal numbers, if I add 1 plus 2, I get 3. If I add 2 plus 1, I get 3. It doesn't matter what order I take them in. Okay, that's the addition rule. So let's say that I give you A is equal to 3 in the x hat direction, right? And B is equal to, let's go 4 in the, at 60 degrees, okay? And I want to know how far from the origin these two, the sum of these two vectors are. This is super, super important, okay? First of all, you walk the vectors from their tail to their tip. So I have A, and I write A. If I walk from the origin to the tip of A is positive. Going from the tail to the tip is positive. Then I walk along B, from the tail to the tip of B. That is also positive. Then I'm going to draw, well, let me draw it in red for you. I'm going to draw a vector R, okay? And this vector R goes from the origin to the tip of B. I'm going to put that at some point P. I don't know what that point is, but at P, okay? You always draw vectors with a tail and a tip. When you do plus, okay, you simply lay them together. Tail to tip, and then you draw R from the origin to the tip of the final vector. There could be a million of these vectors, and we just draw R to the end. But notice what I said. When I walked from tail to tip, I said A was positive. Tail to tip, B was positive. Now I'm going tip to tail back to the origin. So I get minus r. And I set that equal to 0 because when I get back to the origin, I have reached 0 again. I haven't gone anywhere. My net displacement is 0. We'll talk about what that means, but my displacement is 0. So from this, you can see that r is equal to a plus b. Okay, as long as a and b are both positive vectors and you've drawn them with a starting at the origin, b starting at the tip of a, and r going from the origin to the tip of b. Okay. Now, further, we say that r is equal to r of x and r of y. So if I draw this again in an xy plane, I can imagine that my r vector looks something like this, and I don't know what this angle is. I'm going to find out what this angle is. Okay. And it has some component rx and some component ry. And I need to figure out what these are in order to find the magnitude of r and to find the angle. Well, rx, it turns out, is equal to ax plus bx. And ax is 3x hat. It's the amount of a in the x direction. These are called unit vectors. So the amount of a in the x unit vector is 3 plus b in the x direction is 4 cos of 60. I don't know what 4 cos of 60 is. Well, or wait, do I? Cosine is a half. Cosine of 60 is a half, right? So this should be 5. But let's put it in our calculator. Cos times, or 3 plus 4 times cos of 60 gives me 5. So Rx is 5 in the x hat is what we say. What is Ry? Well, Ay is 0. There is no y component to A. Plus By, and By is 4 sine of 60. Sine of 60 is root 3 over 2, so it's 2 times root 3. But you can just do 4 sine of 60 degrees, 3.464 in the y hat. So this is 5, and this is 3.464. Now, r magnitude is the square root of rx squared plus ry squared. And that I can do. That's 25. 5 squared is 25 plus, so square root of 25 plus 3.464 times 3.464, I get 6.083. So my magnitude is 6.083 units, whatever my units are. What is my angle? My angle is arctan of ry over rx, which is arctan of 3.464 divided by 5. And I get 34.7 degrees. Okay. Now, I could have also gone B and then A. And I would have gotten the same exact answer. Why? Well, Rx would still be the X component of B and the X component of A. And Ry would be the Y component of B and the Y component of A, which was 0. So it wouldn't matter what order I added them in. That's really important, okay? This is also an example where we could pick up A and move it anywhere we want. We can pick up B and move it anywhere we want as long as we don't change its direction with respect to the origin and we don't change its magnitude, okay? We don't rotate it at all and we don't change its magnitude. Now, we've just done this next slide, which this next slide is vector addition algebraically, but I want to show you something really important, okay? So this is my origin, this is positive y, and this is positive x, right? So let's say that A is 1 in the y hat direction, and B is 1 in the x hat direction, and C is -1 in the y hat direction, and D is -1 in the x hat direction. So this will be A, I go up 1, B is going to the right 1, C is going down 1, and D is going back to the origin 1. If I want to know what R is, well, R is 0. I can see from the picture that it ends up there, but R is actually equal to A plus B plus C plus D, which is equal to 1 y hat plus 1 x hat plus -1 y hat plus -1 x hat. And if I add these all together, I get 0 in the x hat plus 0 in the y hat, right? And it sits right on top of it. All well and good. However, you can do this for yourself. Choose any order you want, okay? Let's do CADB. So we'll go CADB. So C is -1 in the y. So I'm going to go down 1 in the y. This was my C. And I said CADB. So A is back up 1 in the y. And then D is -1. And then B is that. So I can see that any order that I do these things, I'm going to come back to the origin. And you can try it. Try any combination of those 4 that you want. They're all going to take you back to the origin by the way that they're defined, okay? That's important. There's no order, specific order of operation for addition. Something else I want to show you is that, in fact, if I have some vector, and we just saw this, but in a weird way, but let's say I have a vector that I'm going to call, I don't know, let's call it B just for whatever. Okay, and B is at 30 degrees. All right. Negative B, this negative vector, is actually in the opposite direction. So negative B would be at 180, so at 210 degrees. It points in the opposite direction, okay? And if we want to add, if R is equal to A plus B, and let's say that A is, let's say that A is 1 in the X direction, and B is 1 in the Y direction, just to make it easy, okay? R would then be 1 squared plus 1 squared, which would be square root of 2. And it would be at an angle of 45 degrees. The angle would, and I know that because if I go 1 and 1, it's at 45 degrees. But now let's say R prime is A plus negative B. Now if I draw R, I have A plus B, right? And this is my R. If I want R prime, which is A plus negative B, okay, well then A plus negative B, right? So negative B goes in the opposite direction of B, and R prime would have the same magnitude as R, root 2, but it would be at negative 45 degrees. Its angle would have actually changed. You'll never know until you do the math if the angle changed, if the magnitude of R changed. The point here, though, is that adding a negative vector is the same as subtracting a vector. Furthermore, I want to go one more step on this. Remember how I said to do this, and let's do this one more time. Let's say the store is here, and you're going to walk, right? 2 blocks up and 2 blocks over, or let's call this 3 blocks over, okay? And so where is R? How do I find R? Well, this is 2 plus 3, but R goes like this, okay? And it's the same with going 2 or 3 and then 2. Now let's say, however, you normally walk to the store this way, and you tell me how to go to the store, and you tell me to go north 2 blocks and to go west 2 blocks. Where do I end up? Well, what you did was you gave me the negative vector, right? So I went up 2 blocks, and then I went the negative 3 blocks. I actually ended up way off. I ended up over here, right? So adding a negative vector changes everything. It's simple. You just flip the direction. You still attach the tail of B to the tip of A, but you flip the direction, okay? That is vector subtraction. So vector subtraction, we write that A plus B is equal to B plus A, and A minus B is equal to A plus minus B, okay? That's all you have to know. You just flip B by 180 degrees if you want to subtract it. That's all. And that's really it for vector addition and subtraction. They basically work like normal numbers. The only thing that you need to remember is that you can take components of them and you add the components, then you multiply to get the magnitude. You take the square of the square root of the sums of the squares of the individual components. We did all that. That's all pretty easy to understand. Visually, when you add vectors, you assume that starting at the origin, if you're going in tip to tail, the vector is positive, tip to tail is positive. You always do that, and then you draw R from the origin to B. If I walk this, I get A plus B minus R is equal to 0. So if I walk backwards of any vector, I get a negative. Now imagine this. Imagine this was A, and you drew this as minus B, right? And then you drew R to the tip of B. What would this be? This would be, if I walk A, and then well, let me not call that minus B. Let me just call it B here. I would have A minus B minus R is equal to 0. And what I'd have is A minus B is equal to R. Now, is that going to be the same? What's happened here? Okay, that's not the same because B is not the same. What if this was a negative B? Well, then this would become a positive, be a negative negative. And I would get A plus B essentially is R, or A minus minus B is actually technically what this is. A minus minus B is equal to A plus B is equal to R. Okay, you got to be careful with the negative signs on these vectors. We're going to do a vector lab, our third lab, not this week, but the following week, is all on vectors to get some practice on adding, subtracting, and multiplying vectors, okay? Just keep that in mind. It is confusing, I know. You have to really understand. It really helps with negatives, with subtraction, to draw. And you always draw them. This actually is technically wrong because if I said A minus B, what you should draw is A minus B and then R, okay? And that's very different than this R that we've gotten here, right? And you can see that. A minus B is not the same. If you did this A and then you flip this, your R would be over here somewhere, right? So just keep in mind where you're going to mess up is going to be with the negative signs and not choosing them correctly. Anyway, we'll go back through and I'll show you, we'll look through the review part of the chapter before we leave. But now I need to talk about the new stuff. This is definitely, even if you've done all this vector stuff before, this stuff may be brand new to you. It's multiplying vectors. So what would you do if I told you that A looked like this, and it was at 20 degrees, and it was a magnitude 4. It was 20 degrees off the x-axis, had a magnitude of 4. And B was 110 degrees off the x-axis, and it had a magnitude of 4. And I wanted you to multiply A times B. What would you do? How would you do it? How can you multiply two vectors together? Well, the answer is actually much more complicated. There's two very different types of multiplication for vectors. This is where they do not act like normal numbers, mostly because they have components and unit vectors. The first type of multiplication is actually the multiplication that you're most familiar with, that you've been doing all your life, with an added wrinkle. So let's first review what we've already learned. A is composed of AX and AY. And B, and I know that looks like an R, I'm sorry. And B is composed of BX and BY. You can see here that AX would be along the x-axis, and AY will be along the y-axis, and BY and BX. And BX had better be negative. So these are 4 cos 20, and we'll put the little x hat. I won't always do that, but I really should. Sine 20, y hat. And this is 4 cos 110 x hat plus 4 sine 110 y hat. Okay, and let me do those real fast. 4 cos of 20 is 3.76. So this is 3.76 x hat plus 4 sine of 20 is 1.368 or 1.37 y hat. Are those right? Should they both be positive? Yes. The x component of A is positive. The y component of A is positive. Now, the x component of B had better be negative. So what is 4 cosine of 110? Minus 1.37 in the x hat plus BY had better be positive. 4 sine of 110 is 3.76. 3.76. Now, here's something interesting to note. Could I have done this without doing my calculator for the B's? Yeah, because it's 90 degrees off, right? They have the same length. When I moved it to here, right? X and Y have the same length, they just flip signs. If you don't understand it, it's fine. Put it in your calculator. If you get why that is, good for you, okay? That's really good if you do understand that you're just rotating it through 90 degrees. And when you rotate it through 90 degrees, the lengths flip and you get a flip of your sign. Anyway, that's not super important. It's important for the math people. Everyone else, don't worry about it. So we want to do multiplication. We want to multiply A times B. What we call this is, we call this A dot B. And this might confuse you as well. There are several definitions of the dot product. They have things in common, and they have things that are very different, and they're used for different ideas, okay? What I need to draw is I need to draw A and B as a scalar product. When I do that, I draw them tip to tip. So I know that from the x-axis, this is 20 degrees, and this is my A. This is 110 degrees, right? From the x-axis, and this is my B. What is the angle between them? Well, it's 90 degrees, okay? A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between A and B. And the angle between A and B would be 110 minus 20, which will give you 90, okay? Now, Cosine of 90 is what? 0. And that should tell you what is happening here. This is 4, right? And this is 0. So our answer is 0. Is it a vector? No. The scalar or dot product gives you a scalar. It just gives you a number. We're going to use it for something called work, and work results in energy. Work is force times displacement. Don't worry if you don't know what those mean yet, but when you multiply the force times some distance that you apply the force for, you get a dot product, and that dot product results in energy, and energy is a scalar. So whenever you dot things, you get a scalar. And what it really is let's do another dot product. And this one we're going to do in a different way. Let's say that A is again 4 and B is also 4. But now B is going to be at any theoretical angle. And we're going to look at what will happen. So we know that A dotted with B, and we had to put them tail to tail, is equal to A times B, the magnitudes of these, times cosine of the angle between A and B. Now, when A and B are on top of each other, the angle between them is 0. So if angle A and B were, let's say, 0 or 90 degrees, we know that cos theta is here 0 and here it's 1. And so A dot B is equal to A times B if they're right on top of each other. And if they are perpendicular to each other, when this is 90 degrees, just like it was here, if B is straight up and A is along the x-axis, B is along the y-axis, you get 0, right? That should show you exactly what is going on, okay? What it is the part of B, the component of B that is parallel to A gets multiplied by A, okay? Or another way to say it is, we're going to see, their components multiply, and you just add the result together. You sum the result of the product of the components. What if this was 45? Well, cosine of 45 is root 2 over 2, and this would be A times B times root 2 over 2, because it's cosine of 45. This would be 16 divided by 2, so this would be 8 root 2. I don't know what that is. I don't really care what that is, but 8 root 2. Okay. Now, any other angles, you can see as B gets closer and closer to being perpendicular, the dot product becomes less and less and less. So what the dot product really is it's a measure of how much B and A are parallel to each other. Another way to think about this, and this is probably the best way I can think of, and we're going to come back to this again and again, but imagine you had to push a car or push anything, right? But just imagine you're pushing on a car that's stalled. Your car is stalled and you're trying to push it, right? And your friend's also trying to help you push it. You're pushing straight this way and your friend is pushing at some angle. Well, some of what your friend's force is actually pushing upward and not helping you push in the direction that you're trying to make the car travel. So what you need is you need the parallel part of A and times B. And so another way to write this A dot B is A parallel B cos theta. And how we can see this, again, graphically, is if we have A and we have B, right? Let's write this another way, and that is A B cos theta is A B parallel. I'm so sorry, you guys. It's really late and my brain's on autopilot. So we can write this as A B parallel, the parallel part of B. B is a vector that's made up of B parallel to A and B perpendicular to A. We already have a name for that. We call this BY and we call this BX. And we know that BX is B cos theta, where the angle between A and B is theta, right? So what we get here is that A dot B is really equal to, if A lies along the x-axis, A times B parallel, which is A times B cos theta, which we've already written as ABX, okay? What I'm trying to get at over and over and over again here is that when you do a scalar product, you multiply the parallel parts, okay? It's something called a projection. It's a projection of B onto A. Think of it like a shadow. If I have B here and I have A here, and I shined a light straight down, it's how much of the shadow of B falls on A. Because A could be, let's say A is 40, and B is only 1, right? If I wanted to cross A and B here, or not cross, dot A and B here, and if B were 1, and this angle were 30 degrees, let's say, A dot B would be A B cos of the angle between them, which is 30. This would be 40 times 1 times cos of 30. And cosine of 30 is root 3 over 2. That would be 20 root 2, or 20 times root 3. You could do that in your head, or I mean on your calculator. All well and good. The point being that you're just multiplying the parts that are parallel. There's a better way to see that though. And that's the scalar product by components. So A dot B is equal to AX times BX plus AY times BY. If they had more than 2 dimensions, if you had them in the Z plane, you would have AZ plus or AZ BZ. On and on and on. You could have as many dimensions as you want. It doesn't matter. You just multiply their components. Now, I should also say this. So let's say that AX is 4 in the X hat, and BX is 2 in the X hat, and BY is 2 in the Y hat, for whatever reason. I don't really care. And I don't know the angle between them. I can find the angle between them actually, and I'll show you how to do that. But these are the components I'm given, and I want to know what A dot B is. AX is 4x hat times 2x hat plus AY is 0. There is no AY. So this is 0 times 2y hat, right? And I'm leaving these terms off because this term is also 0. So this term goes away, and what I get is I get 4 times 2 times x hat times x hat, okay? These become 1. X hat times x hat gives you 1, and it just goes away. So what we get is we get 8. There's no x hat there, there's no y hat, it's a scalar. We simply get 8. The answer is 8, okay? Now, what if we wanted the angle? How would we find the angle between them? We know that A dot B is equal to A times B times cosine of the angle, or cosine of the angle is equal to A dot B, I'm sorry, AB, A dot B over AB. Now, A and B, we can find A, the magnitude of A, it's just 4. It's only got 1 component. The magnitude of B is 2 squared plus 2 squared. 2x hat squared plus 2y hat squared. This is root 8, right? Okay, so what we get here is we get that the angle between them is arc cosine, taking the arc cosine of both sides. A dot B was 8, A is 4, and this is root 8, okay? 4 times root 8. So that is 2 over root 8. You can do that on your calculator. arc cosine of 2 divided by root 8, and I get 45 degrees. The angle between them is 45 degrees. That should make sense to you. Right? How that would make sense to you? Well, draw them. A is along the x-axis. B is 2 and 2. So if I go 2, well, actually, I would only go half the distance, and then I go up 2, right? 2 and 2. I can easily see that this is 45 degrees, and therefore the angle between A and B is 45 degrees. However, it's good that my math worked, and I could solve it that way, okay? So the main takeaways here are that there are really two different ways to do the dot product. They are A, B cos theta, and A dot B is AX, BX plus AY, BY, right? They're both the same, they're equivalent. They both give you a scalar. You can do it by illustration with projections. Now, what if I had A here and I had B somewhere like this, okay? And I wanted to know the angle between them. Well, I can actually always assume that there's some x-axis along A, and if I know the angle between them, let's say I don't really know how far this is, but I know the angle between them is 20 degrees. Then A dot B would be A, B cosine of the angle between them, which is 20 degrees, right? That's it. B is always the projection or the amount of A or B along A or parallel to A, or the amount of A parallel to B. So let's look at that really fast, right? Now, what if we flipped them? What if A were here and B were here and this was 20 degrees? A dot B is still A, B times cosine of 20. It doesn't matter the order of A and B because it gives you a scalar, and a scalar has no direction. However, there is another type of multiplication. And this other type of multiplication is something called a cross product. And this is where things get really weird, really wonky, and really hard, okay? But we're gonna do something called torques eventually. And when we do torques are a lot like forces, but they end up making systems rotate. The cross product happens when you have two vectors that you're multiplying, which cause a rotation. And you have to draw them differently. So for the scalar product, we drew A and B at the same origin, okay? We drew their tails at the same origin. For the cross product, you do the same thing, but it's actually easier to visualize it this way. Let's say I have a vector A, and at the tip of A, I'm applying a vector B. You can see how this would push on the vector A and cause it to rotate that way, right? Imagine A is a rod and B is a force. So this is a distance along the rod, and this is a force. It would cause it to rotate around if that rod were attached in a way that it could spin. You can think of, you know, pushing on the edge of a wheel, right? You push on the edge of the wheel with your hand at some r distance from the center, r, and this is a force, and this causes the wheel to spin around. That's what cross products do. And we write them as A cross B, okay? And we draw them tail to tail. However, there's something very important here, okay? The very important thing here is that A cross B, unlike the dot product, in the dot product, A dot B is equal to B dot A. In the cross product, A cross B is not equal to B cross A. And furthermore, what A cross B means is we turn A to B, and that'll come up later, but we go from A to B. If we're turning from A to B, this is a counterclockwise rotation. If we're turning from A to B here, it's a clockwise rotation. We'll talk about that in a second. But before I do that, I've already said, what do cross products do? I'm going to come back to this in a second. I want to talk about the right-hand rule. This, I've had students who kind of made up their own rules to this. You already know everything about the right-hand rule. You just don't know the right-hand rule. Now, ever since you've been doing math with graphs, I know you all, okay, well, I don't know, some of you may have learned from a weird system from somewhere else. I'm assuming that you all have drawn your graphs with the x-axis positive here and the y-axis positive here, okay? And you take angles as you go around. This is what we call counterclockwise on old clocks with hands, right? As you go this way around, it's going the opposite direction that the hands of the clock move. Okay, so this is a positive theta, or a positive change of angle, is counterclockwise. Okay, second thing to remember. When you do three-dimensional problems, x, y, and your z goes up, right? So this is the y-axis. You can imagine that this is the same exact graph that you're looking at here, but your eye is looking at it, you know, straight down. Okay, you're looking straight down at it. So z actually comes out of the board, what we call out of the board. It has to. You have to go in this order, x, y, z. This would be negative x going into the page, negative y, negative x, negative z. But here, z is positive coming out towards you. Now what I want you to do is with your right hand, I want you to hold your right hand, and I'm going to turn my hand backwards so that it's pointing correctly at you. Your thumb, right, should be pointing, well, okay. This is going to be weirdly backwards to you, but remember that it's backwards on the camera. Your thumb points at you, okay? Take your hand, your right hand, point it at yourself. How your fingers curve, naturally when you make a fist, they curve in the positive direction. When that happens, okay, if you lay your palm flat towards the ceiling, your hand is along X. As it turns towards Y, it's curling positive, and your thumb points in the positive Z direction, out. That's why we call it the right-hand rule. X, Y, Z follow like your right hand would. Some people do this where they point like one finger up, their thumb towards you and their other finger. Don't do that. All I want you to know in this class is right hand. If your thumb is pointing towards you and you see it curling in the natural direction of making a fist, it's positive Z. If you have to put your thumb into the page, into the camera, and my fingers curl the opposite way, clockwise, that is negative Z, okay? Why we need to know that? We need to know that because we need to determine which way the cross product is causing a rotation. It's a bit complicated, so before we do that, cross products cause rotations, and that's why I would think about it as, imagine, like I said, you have a ball that's attached to a string that has an axis here. And this is a vector R that goes from the axis of rotation. So it can swing around and it gets hit by a force. I would take R cross F and that would tell me the rotation. It gets a little complicated and we're going to have to go through that, but cross products result in rotations. Rotations. And furthermore, they are vectors. However, the vector is along a perpendicular axis to both R and F, or if you have A cross B, totally symbolic, then the cross product is along a C hat vector that is perpendicular to the plane that A and B are in. When we talk about X and Y planes, so we put vectors in 2 dimensions in an X and Y plane, which is the normal case for the class, you need to determine if the cross product is in the positive Z or the negative Z, into or out of the page. Now, here's the problem though. Are these actually vectors? Are rotation vectors actually vectors? For those of you who are really good at math, guess what? They're not actually vectors. When we do rotations later on, the book will talk about it. It does an okay job. It doesn't quite get it right. Essentially, if you try to reflect them under certain reflections, the rotation vectors don't act like other vectors do, and that's a huge problem. So rotation vectors are kind of pseudo-vectors. However, the cross product, when used for any vector, not just motion, so when you're not talking about rotation vectors, the cross product by itself always gives you a vector that is perpendicular to both A and B, okay? Or perpendicular to the plane of A and B, I should say. If that doesn't make sense to you, it's okay. We're going to review all of this one more time when we get to torque, and we have to do the right-hand rule all over again. For now, it's enough to be introduced. If you're starting, I think 4A or maybe 4C, I'm not sure which one of them. One of them I think is doing cross products and dot products right now. So again, there are 2 ways to do it. I'm actually going to flip these because I want to do the trigonomic first. Remember that the A dot B was A, B cosine of the angle between A and B. Well, now A cross B is A, B sine of the angle between A and B. And this will give you a vector in the Z hat direction, okay? If A and B are in the X and Y hat only, X and Y planes only, okay? Let's imagine, we'll go back to the one that we did, except we're gonna do 2 of them. So here we're gonna have B is 4 and A is 4, and they are 30 degrees apart. And here B, sorry, imagine A is drawn like that. Here now B is 4 and A is 4, and they're 30. Okay, and we want A cross B in both cases. Now A cross B, I get A turned to B, which is A times B times sine of the angle between A and B. What is the angle between A and B? It's positive 30 degrees. Okay, this gives me 4 times 4. What is sine of 30? It's a half. So this gives me 8 in the positive Z hat direction. By the right-hand rule, you're turning, A is being turned to B by the cross product. That's the same if you curl your fingers in that direction. This A cross B vector comes out of the page in the positive Z hat direction. Here, we get A, B, sine of the angle between them, but the sine from A to B is negative 30, right? You're going in the negative direction. And that brings up something kind of important that I need to bring up right now. If you don't know this already, cosine of theta is equal to cosine of negative theta. Why that is if you reflect, if this was 30 and this was negative 30, it doesn't matter if you're taking cosine of 30 or cosine of negative 30. Sine of negative theta is negative sine of theta, okay? just remember those. So this ends up being negative 4 times a half, which is negative 8 z hat direction, or 8 z hat negative direction, which means this one goes into the page in the negative z hat direction. A cross B in this case is negative because we're rotating A to B in the negative or clockwise direction. By the right-hand rule, that is a negative rotation, and it picks up a negative sign using the trigonometric formula for the cross product. There's another way to do it though, and we'll do both those this way too. You may not know matrices yet, and it's okay if you don't. But the easiest way to remember the component version of A cross B is actually to do what's called a determinant of a matrix. And you write you write X, Y, and Z. You write AX, AY, AZ, BX, BY, BZ, okay? A cross B is the determinant of this matrix. How you do this is you write times the X hat plus something times the Y hat plus something times the Z hat. What those somethings are is starting here, you do AY times BZ minus BY times AZ. Okay, so you just do this cross and this cross. Oh, shoot. So forget that for a minute. For when you do Y, you forget the two below. So when we did this, we forget about AX and BX, BZ. So you just take those away and you do what we did. All right, so when we do Y, forget about these ones, and you cross these, but it picks up, it actually picks up a negative sign. Every other column picks up a negative sign. So this becomes BX AZ minus AX, and this should have been BZ, BZ. All right, get rid of this again. And now when we do Z, we just worry about the columns of X and Y. And if this doesn't make sense to you, it's okay. You won't need to use this. You can just write this formula down and memorize it. But once you get to linear algebra or cross products where you're doing matrices, you get this stuff. Now, before, in our previous example, notice that A and B, at least in example 1, A had AX and AY, and B had only BX. This is our first, oh my gosh, I am so sorry, you guys. It's just BX plus BY. Okay, so here A has an X component and B has an X and Y component. But there's no AY component, so this one goes away. There's no AZ component, so this one goes away and this one goes away. There's no BZ component. And the only thing we get, A cross B, and I know there's X's flying around, is equal to, there's nothing here, there's nothing here, and all we get is AX times BY in the Z hat direction. Now remember that BY was B sine of the angle between A and B, right? So this is B sine of 30. And this is exactly what we got for that first guy. This was AX, I'm sorry, this was A times B sine theta, which was 4 times sine of 30, right? And there you go, you get 8 times or 16 times a half. You get 8 in the z hat direction, positive. Now, when we go and do this one, right, B has only an x component. A has a y component. I'm going to redraw this for you. Okay. So this becomes A, y, b, x. And now look what we get. There is no by. So this goes away. And A cross B becomes negative ay bx in the z hat direction, which is again negative a sine of the angle between A and B times B, right, in the z hat direction. AY is 4 sine of 30, not 4 sine of negative 30. So from the components, it will pick up the proper negative sign if you do it component-wise in the correct way. That's important. But really, all you need to remember is a couple things. So let's kind of write these down. So A plus B is equal to B plus A. B, A plus negative B is A minus B, okay? And A is equal to AX plus AY. Then A magnitude is AX squared plus AY squared, where AX is a cos theta and AY is a sine theta, and therefore theta is arctan of AY over AX multi-value. A dot B, which is a scalar, it's just a number, is equal to AB cos of the angle between A and B, and it's also equal to B times A, and it's also equal to AX BX plus AY BY. A cross B is a vector. It's equal to AB sine of the angle between A and B in the z hat direction, as long as A and B are only in x and y components. This is also equal to this whole thing that I'll give you. But A cross B is equal to negative B cross A. You can check that for yourself. And further, A cross B, if A and B are only in the x and y direction, is equal to AX BY minus BX AY in the z hat direction, okay? So if you can remember all those things about vectors, you're good. Also remember SOHCAHTOA, which is sine of the angle is x over hypotenuse, cosine of the angle is y over hypotenuse, and tan of the angle is y over x. There's a few other little things to learn in this chapter, but in general, that's really all you needed to remember. A lot of it's just right triangle stuff and addition, so you already know it unless you're rusty on your right triangle trigonometry stuff. The scalar products we'll use when we get to work, which we won't need until after exam 1, but they're here now. You're probably learning them a little bit now. The cross product stuff is all for torque, which we also won't learn until we get to like chapter 10, okay? So we're gonna go back over all this stuff. I don't want it to scare you. And I know it's a lot of horrible math, and I don't want that to scare you either, because starting next week, we'll be going through real problems that are dealing with velocity and displacement and acceleration. We're gonna have to use this stuff over and over and over again, but you'll get more comfortable with it the more you use it if you haven't used it too much yet. So one last thing I wanted to do was maybe go and look at a couple of these problems. So I think I closed, I did. So I'm back in the Canvas resources. I'm going to Wiley. I'm going to go to campus-wide resources, and I'm going to do additional sample problems, let's say. And I don't know if this is going to give me, oh yeah, there's something that we can talk about later, but these nested products, I do want to talk about right now. To be honest with you, I don't really feel like doing too many problems on this. I've done enough already, I think. But if you go through these sample problems, they're pretty good. They'll give you the answer. It tells you evaluate 2 times the vector A, 2B plus C, crossed with -3DC. So actually, let's do that one, because I do want to talk a little bit about this. I'm just going to go to a brand new slide. One thing that I should say before we do this sample problem is notice something, that if I have A dot B cross C and I have A cross B dot C, there is an order of operations here, okay? Cross products can only be between 2 vectors. They have to be 2 vectors, and you end up with something that's perpendicular to both vectors. Therefore, they have to be done first. You can't cross a scalar with a vector. Why? Because the cross product is a rotation, and there's no direction of rotation if you're crossing a scalar. You can always multiply, which is technically a dot product. You can multiply a scalar times a vector, but you can't cross a scalar and a vector. So this and this are automatically true. If you tried to do A dot B first, you would get a scalar, and you would be trying to cross a scalar with a vector, and that doesn't work. All right, so let's do, I'm going to do this. I'm just going to share my desktop. Okay, and I want to go here, and I want to look at this really fast. So let me move. So I don't want to do that. I want to shrink this down so that I can see it. All right. And then I'll just down. All right. So this thing tells us that we want to do -2 times A dotted. It's hard to tell, but that's a dot with 2 times B plus C crossed with -3D. And right below this, it gives us what all these are. Okay, so let's do this. We'll do the parentheses first. So 2 times B plus C is equal to what? Well, this is 2 times I hat minus 2 times J hat, multiply 2 through, plus negative I hat plus J hat. What I get is I get I hat minus J hat, if I did that right. All right, and -3D hat, right, is, oh, and I should note, if you don't know already, I, J, and K are just another way of saying X, Y, and Z. So 3D is -3 I hat minus 3 J hat. And I want to cross these two. I'm going to cross this product with this product. And so my cross product, A cross B, remember, was AX BY minus bx, ay in the k hat or z hat direction. Okay, these are i's and j's, i's and j's. Okay, so a cross b is this 1 times minus 3. So I get minus 3 minus 1 times minus 3 with a minus sign, which is minus 3. So minus 3 minus 3. Okay. Let's make sure I did that correctly. This is minus 3. This is minus 1. This is 1, and this is minus 3. So yeah, I get minus 3 minus a 3 in the k hat direction, which is minus 6 in the k hat direction. Okay. From that, I now want to do, the final thing that I want to do is minus 2 a hat dotted with this product, dotted with minus 6 k hat. Now, when I dot things, I multiply their components. So I would do whatever a I hat plus this whole products I hat, etc. So the only thing that I need to worry about here is the k part of a. So this ends up being minus 2 times a in the k hat times minus 6 in the k hat. And a's k hat is 1. So this is minus 2 times 1 times minus 6, and I get 12. 12 is my answer to this. And you can go through this, and you can do it all. And why did I drop, where did I drop a minus sign? They're saying that we should have gotten a minus or a positive 6 here. Did I forget something here? I have I minus j crossed with 3i plus 3j. So somehow I missed this minus 3d. Oh, I missed a minus sign here. So yeah, there's a minus sign. I'm sorry about that, you guys. These are pluses. And that means that these both turn into pluses. And this is a plus 6, so therefore this has a negative sign. Sorry, I dropped that negative sign up there. Okay, but the answer is negative 12. The point being that when you do this one, for the most part, they follow the same old rules of arithmetic that you've been doing. Do the stuff in parentheses first, then do the cross products, then do the dot products. It doesn't make sense any other way. If you tried to dot this on this, they don't even need these outer parentheses, because you know you can't do the scalar multiplication between 2a and the product of 2b plus c, okay? You can't do that because you would end up with a scalar, and you can't cross a scalar and a vector. The rest of it is all pretty simple. So if you can do this one, you're great, and you totally understand cross products and dot products. Now, this is what our quiz is going to somewhat look like next week. You'll have some kind of dot product or cross product. It won't be this bad, but it will be something like this. So I suggest just at least make sure you know this problem, maybe one of the other sample problems. There's also these where they're doing illustrations, their work doing. As I said, we're going to get a homework on vectors tonight. It'll probably be 6 or 7 problems on vectors on chapter 3. And if you struggle through the vector stuff, it's okay. We're going to do a lot of vector stuff. And then we're even going to do a lab on it in a week from Thursday. So I feel for you. Good luck, and I'll talk to you all soon.